Welcome to the RhinoCAM Quick Start tutorial series, brought to you by MecSoft. Today we'll be introducing 4-axis milling. If you would like the source files used in this video, just drop us an email at support@mecsoft.com and ask for the intro video source files. We'll be happy to send you a download link. There is a completed version of this part located in the same folder that you can refer to as needed. It represents how your part should look upon completion of this tutorial. Before starting any new CAM project, you should first perform the following startup checklist. For more detail on each of these items, you can refer to the 3-axis introduction companion video. Also, before learning 4-axis operations, it is recommended that you first become familiar with the setup and generation of both 2-axis and 3-axis operations. Introduction videos for both 2 and 3-axis are available. We will perform the following basic steps in machining this model. First, we will define the machine and the post-processor to use. Then, we will define the machining setup, including the stock geometry, material, and additional table rotation setups. We will then load a predefined tool library. Then we will generate our initial 3-axis horizontal roughing toolpath. We will then rotate our 4th-axis table 180 degrees and generate an additional 3-axis horizontal roughing toolpath. Then we will reset our 4th-axis table back to 0 and generate a 4-axis parallel finishing toolpath. Also, we will simulate and post-process each of our toolpaths. Okay, let's start by defining the machine to use for this job. From the Program tab, select Machine to display the dialog. Under Machine Type, set the number of axes to 4-axis and set the configuration to Table. Under 4th-axis parameters, set the rotary axis to +X and set the rotary axis angle limit to no limit. This means that our 4th rotary axis will extend along the center of our part in the positive X-axis, with the ability to rotate a full 360 degrees. When this dialog is displayed, the 4th primary axis is indicated on the graphic screen. Pick OK and notice that the machine type now appears under the machining job in the machining browser. Next, we'll define the post processor. From the Program tab, select Post to display the dialog. For the current post processor, select HOS from the list of available posts. Then set the posted file extension to NC. Other file extensions are available depending on your machine requirements. Pick OK and notice that the post type now appears under the machining job in the machining browser. Now, let's define the machining setup. If there is no setup one listed under your machining job, the system automatically creates one when a work zero or an operation is generated. However, by default, the MCS, or Machine Coordinate System, is already aligned with the WCS, World Coordinate System, so this step is not required for this part. However, in production, you can have multiple setups and assign different machining orientations for each. In this step, we'll define the raw stock from which to cut the part. From the Program tab, select Stock, and then select Box Stock from the menu to display the dialog. For the stock dimensions, we'll set the length to 9.75 and the width to 3 and the height to 3 also. Note that the stock dimensions you enter here are measured from the corner of the bounding box selected in this dialog. Pick OK and notice that the stock type now appears under the machining job in the machining browser. If the stock does not display on the screen, select the Stock Visibility icon located at the base of the machining browser. Once the stock model is created, you can move it in alignment with the part if needed. From the Program tab, select Align, and then Align Stock from the menu to display the dialog. We will be removing material from all sides, so for Z alignment, we'll select Center, and for XY alignment, we'll also select Center and then pick OK. The stock is now centered about the part. We can see that the height of the stock leaves extra room to cut the part from all sides. Next, we'll set the material for the stock geometry. From the Program tab, select Material to display the dialog. For material, select Wood from the list of available materials and then pick OK. If the material texture does not display on the stock, select the Material Texture Visibility icon located at the base of the machining browser. Material texture is only for display purposes, and for this part, we will leave it toggled off. To save time, we will load a predefined tool library. From the Tools tab in the Machining Objects browser, select Load Tool Library to display the File Open dialog. We'll select the predefined tool library named 4-Axis Introduction Tutorial.vkb that we have located in the default data folder and then pick Open. If you would like the source files used in this video, just drop us an email at support@mecsoft.com and ask for the intro video source files. We'll be happy to send you a download link. The message says that 2 tools were added, and we see that a 1/4 inch flat mill and a 1/4 inch ball mill appear in the Machining Objects browser. If you double-click on one of the tools, you see it displays the Create Edit Tools dialog with its dimensions and speeds and feeds parameters already defined. We will be using the 1/4 inch flat mill for our horizontal roughing and our 1/4 inch ball mill for our 4-axis parallel finishing operation. Now, let's discuss our approach to machining this part. You can see that we have added a 1/4 inch cylindrical core along the center of the part that extends out the full width of the stock. This will serve to anchor the part to the stock during machining. You can also see that we have added a planar rectangle at the center line of our part on the XY plane. This will serve as containment for our 2 horizontal roughing operations. In our initial setup 1, we will use a 3-axis horizontal roughing operation to rough out the part from the top of our stock down to the center line. We will then create setup 2 that indexes our rotary table 180 degrees and then use a second 3-axis horizontal roughing operation to rough out the part from the bottom of our stock up to the center line. We use the terms top and bottom for display purposes only. The actual stock on the 4-axis CNC machine will be rotating along the x-axis. Once the second 3-axis horizontal roughing operation is complete, we will then create a setup 3 that will index our rotary table back to 0. Then we will program our 4-axis parallel finishing operation. During this operation, the rotary table will index a full 360 degrees to finish the entire part along the x-axis. So if you're ready, let's get started. We will begin with a 3-axis horizontal roughing operation with the rotary table set to its default index of 0. This is labeled Setup 1 under the machining job in the machining browser. From the Program tab, select 3-axis and then Horizontal Roughing from the menu of 3-axis operations. This will display the Horizontal Roughing Operations dialog. By default, the Control Geometry tab is displayed first, allowing you to define drive and/or containment regions. In 3-axis, this tab is basically used if you want to contain your toolpath to a specific area of the part. We'll select the Drive Regions tab and then pick the Select Drive Containment Regions button. The dialog will minimize and we'll select the planar rectangle that we created at the center line of our part in the XY plane, and then right-click or press Enter to continue. The dialog reappears and we see that Drive Region 1 was added to the list of selected machining regions. You can verify this by selecting it from the list and it will highlight on the graphic screen. Now we switch to the Tool tab of the dialog and select the Flat Mill 1/4 inch tool from the list of available tools. Note that the tool parameters of the currently active tool are always displayed in the status bar at the bottom of the Machining Objects browser. Now we switch to the Feeds and Speeds tab. select the Load From Tool button. The system will retrieve the feeds and speeds parameters that were set when the tool was defined and associate them with the current operation. Next, we'll switch to the Clearance Plane tab. Set the clearance plane definition to Automatic and the cut transfer method to Clearance Plane. In the automatic mode, RhinoCAM will determine a safe Z height for locating the clearance plane. Setting the cut transfer method to clearance plane will force all transfer moves to be performed in this determined clearance plane. This dialog is active. The clearance plane is shown on the graphic screen. Now switch to the Cut Parameters tab to control the cutting. We'll leave the tolerances set to 0.01 or 10 thousandths and leave the stock set to 0.025. This means that we will be leaving 25 thousandths of stock remaining on the part and that the actual tool path cannot deviate from the stock height more than 10 thousandths after machining. For the step over, which is the distance the tool will move per pass in the X and the Y, we'll make it 40% of the tool diameter. You can also specify the step over by entering an exact linear distance. Now we select the Cut Levels tab and set the Step Down control to 50% of the tool diameter. We mentioned that the step over defined on the Cut Parameters tab is the distance the tool moves in the X and Y. Now, the step down specified here is the distance the tool can move in Z. This means that each Z level cut in the roughing operation will remove 50% of the tool diameter, which in this case will be 1/8 of an inch. You can refer to the images in the dialog for information about what each parameter means. Now we go to the Cut Levels section and check the box next to Bottom and then enter 0 in the field provided. We want the depth of our roughing operation to stop at the center line of our part. Next, we'll select the Engage Retract tab. This tab allows you to separately specify motions the tool will follow when it engages and retracts both material and air. For Engage Retract in Material, we'll set the ramp motion to Path and set the ramp angle A to 10 degrees. You can refer to the images in the dialog for information about what each parameter means. Next, we'll check the box next to Always Engage in Previously Cut Area if possible. As the name suggests, if possible, the system will use the in-process stock model to select an engagement point in an area that has already been previously cut. For Engage Retract in Air, we'll select Linear Extension D and enter a value of 0.275. This will extend the engagement point out from the part by 275 thousandths of an inch. Now we'll pick Generate to calculate the toolpath and display it on the graphic screen. Note that the display of the toolpath in the graphic screen can be turned on and off by selecting the toolpath visibility icon located at the base of the machining browser. The new toolpath can now be simulated to display the in-process stock model. Switch to the Simulate tab at the top of the machining browser. Select Preferences and then set the simulation model to polygonal and the simulation accuracy to fine, and then pick OK. Then, under the Preferences button, check the box next to Simulate by Moves. This will speed up the simulation. You can also adjust the slider to further speed up the simulation. Now we select the 3-axis horizontal roughing operation we just created, toggle the display of our stock, and then pick Play to run the simulation. Then we can select the toolpath visibility icon from the base of the machining browser to turn off the toolpath and see the in-process stock model. If you don't want to wait for the entire toolpath, you can select Pause and then To End to calculate and display the entire toolpath simulation. Now with the part roughed out from one side, we will create a second setup to rotate the table 180 degrees so we can rough out the opposite side. From the Program tab, select Setup and then Rotate Table Setup from the menu of Setup Operations. This will display the Rotate Table Setup Operation dialog. For the table rotation angle, we'll enter 180. Select counterclockwise and then pick OK. You will see that Setup 2 was added to the machining job. You will also notice that the MCS triad on the graphic screen is now rotated 180 degrees about the x-axis. Now we'll use copy and paste to create a second roughing operation from the first. Select the horizontal roughing operation we just created under Setup 1. Now right-click on the selected operation and pick Copy. Now select Setup 2 that we just created, right-click and select Paste. This creates a copy of the operation and places it below Setup 2 in the machining job. We want this second horizontal roughing operation to use the same dry region as the first, as well as all of its same parameters. So all we have to do is select the operation, right-click on it, and pick Regenerate. Once complete, we can select the Simulate tab and pick Play to simulate the toolpath on the in-process stock model. As you can see from the in-process stock model, our part is now roughed out from both sides. Now with our roughing operation complete, we'll create a third setup and rotate the table back to 0 in preparation for our 4-axis parallel finishing operation. From the Program tab, select Setup and then Rotate Table Setup from the menu of Setup Operations. This will display the Rotate Table Setup Operation dialog. For the table rotation angle, we'll enter 0 and then pick OK. You will see that Setup 3 was added to the machining job. You will also notice that the MCS triad on the graphic screen is now rotated back to 0 degrees. Now we're ready to program our 4-axis parallel finishing operation. In this method, finish cutting is performed by varying the table rotation continuously as the tool traverses along or across the rotary axis. This method is similar to the 3-axis parallel finishing, except that the cutting is performed in 4-axis mode. From the Program tab, select 4-axis and then Parallel Finishing from the menu of 4-axis operations. This will display the 4-axis parallel finishing operations dialog. From the Control Geometry tab, select Remove All. We don't want any machining region selected. When you do this, the system considers the entire part as one continuous drive region. Now we switch to the Tool tab of the dialog and select the Ball Mill 1/4 inch tool from the list of available tools. Now switch to the Feeds and Speeds tab. Select the Load From Tool button. The system will retrieve the feeds and speeds parameters that were set when the tool was defined and associate them with the current operation. Now we'll switch to the Clearance Plane tab. Set the clearance plane definition to Automatic and the Cut Transfer method to Clearance Geometry. In 4-axis machining, a cylindrical clearance zone is calculated around the rotation axis. In the automatic mode, the system will determine a safe Z height for locating the clearance cylinder. Setting the Cut Transfer method to Clearance Geometry will force all transfer moves to be performed in this determined clearance cylinder. When this dialog is active, the clearance cylinder is shown on the graphic screen. Now we'll switch to the Cut Parameters tab to control the cutting. Under Global Parameters, we'll set both the in tolerance and out tolerance to 0.001 and set the stock to 0. This means that the toolpath cannot deviate above or below the actual part surface more than 1/1000th of an inch. For the cut pattern, we'll select Along Axis, a zigzag pattern, and Low to High. As the image in the dialog illustrates, the cut will traverse along and parallel to the rotation axis in a zigzag pattern, beginning at the end closest to the axis origin. Since we don't want the toolpath to cut into the remaining stock at each end of the part, we will contain it using the Cut Axial Containment section of the dialog. For low value L, we will enter 0.5, and for high value H, we will enter 9.25. Entering these values will contain the toolpath within the area we have previously roughed out. We will leave start angle S set to 0 and end angle E set to 360. This will allow the cut to rotate a full 360 degrees, covering the entire part. Next, we'll set the step-over control to 15% of the tool diameter. Now, we'll leave any remaining parameters set to their default values and pick Generate. Once complete, we can select the Simulate tab and then pick Play to simulate the toolpath on the in-process stock model. Then we can select the part visibility icon from the base of the machining browser to turn off the part during the simulation. Now, with the toolpaths complete, we're ready to post-process to an output text file containing G-codes that can then be sent to the machine tool to actually machine the part. Now, switch back to the Program tab. To post all setups in one G-code file, select only the machining job at the top of the machining browser, and then right-click and select Post All. This will post-process all setups and all operations created under the machining job. By default, the part file name is used as the G-code file name. Also by default, the posted G-code file is saved to the folder where the part file is located. Now pick Post, and the G-code file is displayed in Notepad, where it can be viewed or edited manually. Now close Notepad. Here are some additional selection techniques you can use. When your machining job contains multiple setups, you can select any setup, right-click and select Post to post only that setup. While holding the Control key down, you can select multiple operations and then right-click and select Post to post only the selected operation. For further assistance, you can visit the online help supplied with the program or visit www.mecsoft.com for additional tutorials. Thank you.